Hello everyone, today we are going to look at some basic circuits. Now, if you want to add something in a circuit, for example, a light bulb, a resistor, or battery, you can add it in two different ways. You can either add it in series or you can add it in a parallel fashion. So adding something in series means that you are just linking everything together. For example, in this case, you can see that I have three resistor 1, 2, and 3. They are called added in series because there is only one pathway for the electron to go through. Now, in this situation, what happened is the electron is going to be, now remember from our analogy last day, electron has a backpack. They carry stuff in their backpack. So for example, I have this little tiny electrons in here, and it will, well, at this moment, it has nothing in its backpack. But then it goes through this battery. Now, if it goes through the battery, it will then pick up something. So for example, let's say in this case, it picked up 6 volts, okay, 6 joules of energy. So now you can imagine that it's actually carrying 6 joules of energy. And what happened is it's going to go to travel to here, which is to station number 1. So, or stop number 1 or customer number 1. So at customer number 1, what happened? Well, you're going to have that 6 volts of energy, 6 joules of energy per coulombs of electron. Some of that energy is going to be delivered to this customer number 1. Now, how much? Well, it's hard to say. It actually depends on who is more hungry, which resistor is the biggest. If resistor 1 is the biggest, it will eat the biggest portion. Now, if in a circumstances where all the resistors are exactly the same, then the 6 volt will actually be distributed equally. That means you have minus 2 volt here, minus 2 volt here, minus 2 volt here, and plus 6 volt when you go back to the battery. So this is energy, right? Energy can only be either decreasing or increasing. You cannot destroy or create energy. You can pick up energy from somewhere. You have to put down some energy when you deliver your items. So what we say then is that in a circuit, like something that we call like in series, now it doesn't have to be 2 volt or 2 volt, 2 volt, 2 volt like this. It could also be, so plus 6 from the battery, minus 1 volts in here, minus maybe 3 volts in here, and minus 2 volts in here. Now at the end, you still have a total of 6 volts or 6 joules of energy gone from each coulombs of electron, and the electron pick up 6 joules of energy when it goes back to the battery. So there are different combinations. Now, but what we can say is that the amount of voltage that you get, that you drop from here, 1, 2, and I guess I should say V1, V2, and V3, should always add up to V total. That's the most important thing. So V1, V2, and V3 should always add up to V total. Yes, there is a plus or minus, but it's like saying the word that you pick up something and you deliver something. So when you deliver energy to that resistor or light bulb, to, for example, resistor 1 and light bulb 1, is considered to be negative. But so that's why sometimes we write down this equation. V total equals to V1 plus V2 plus V3, for example, in this case. So the total amount of energy, voltage that you pick up from the battery is equal to the total amount of voltage that you drop at each of those locations. Okay, so now I have an animation in here. So this one, first one, this one. So now if there's only one stop, right? So imagine if there's only one stop, you see an item will pick up. So let's say, look at those electrons after they go through the battery, they will now have like 6 joules of energy on it, right? And then when they go to that only stop, there's only one light bulb, so there's only one stop. So the electron have to drop everything before it comes back. Okay. Now, what if there are 2 stops? Well, when there are 2 stops, then you basically had to give up, for example, if those 2 stops have exactly the same resistance, that means they are, in our Pizza Hut analogy, equally hungry, then you will distribute the amount of energy equally between the 2 stops. Now, of course, it doesn't have to be that way. Maybe one customer is hungrier than the other one. Then you can also have a different amount of voltage drop between the 2 light bulbs. At the end, though, however, how much energy you drop or the amount of voltage that you drop at each light bulb combined must be exactly equal to the amount of energy that you pick up from the battery. So I give you, remember in our analogy with Pizza Hut from last day, if you pick up 6 pizza, you have to drop or deliver all 6 before you come back. I hire you to do a job, I give you 6 pizza, I say deliver them. If you come back with like an extra pizza, or if you come back with like 2 pizza, or if you come back with -1 pizza, something is wrong with you, right? I mean, I give you 6 pizza, you should deliver 6 pizza. When you come back, you should have nothing. So when the electron, look at this electron, this is when they're going back. When they go back to the battery, they should have nothing on it, right? They should have nothing on it. So this is a really good analogy to use. Okay, so now, then going back to here, so now hopefully you understand why voltage must be added this way. Okay, so in a series circuit then, the total amount of current. So let's look at current. Now current is the amount of electron. Now let me draw that electron again, but with a slightly different color. So for example, how much is the current at this point? How much is the current at this point? How much is the current at, let's say, this point, right? So, oh, sorry. You know what? Let me label it this way. So the current goes like this, go in, go like there. Okay. All right. So let me label again. So how much is the current coming out from the battery? So we can say that. And then how much is the current going through the resistor number 1? How much is the current going through resistor number 2? And how much is the current going into resistor number 3? Now let's talk about that. Okay, so now what is current? If you go back to our notes from last day, on the diagram where we have this Mr. Chang's, pizza delivery model. If you remember from this, right? If you start with 2 electrons, so let's say you start with like these 2 electrons helping you deliver your food, then we say this is 2 amp. What does 2 amp mean? 2 amp of current means 2 coulombs of electron is going through a certain point in the circuit every second. Now, so let's say these 2 electrons exit from the battery, so that will be I total 2 amp. As they go through the first house, how many electrons will go through the first house? Now, so let's say this is I total, right? So I total is 2 amp. So I total is 2 amp, meaning I'm sending out 2 groups of electron per second. So how many groups of electron will go through this house per second? The answer should be 2, right? I mean, I send out 2 people. Why would there be less than 2 people going to the first customer if there's only 1 row? It's not like they can split up anything, right? There's only 1 row. The electrons are only allowed to walk on there. So the amount of current going into the first house, I will call I1, must also be 2 amp. There must be 2 electrons going through the first house also. And then how many electrons will go through the second house? 2, because there's only 1 row. I don't know where they could go if they're not going into that house. So the amount of current going to the second house, I2, is also 2 amp. How about the amount of current going through the third house? 2 amp. Because again, there is only 1 row. Where else should they go, right? So 2 electrons go through the first house, 2 electrons go through the second house, 2 electrons go through the third house. And when they come back to Pizza Hut, I expect 2 electrons to come back to report to me because they deliver items for me. If I send out 2 people, how many do you expect to come back? 2 people, right? So the current should be exactly the same in a series circuit because there's only 1 pathway. The electron doesn't disappear. It must go through the row. You know, there's a common phrase that I always like to use. You eat the pizza, which is the voltage, right? As a house, you eat, as the customer living in here, you eat the pizza. You don't eat the person who give you that pizza. Okay, I hope you don't, because I don't. That's cannibalism. That's horrible. In most countries, that's, well, illegal. Okay, you don't eat the person who's giving you that pizza. You don't order Uber Eats or DoorDash, or or some other ones. You don't order stuff from them, and then they deliver you the food, and you eat the person who gave you the food. You eat the food, right? So if I send out 2 people to your house to deliver pizza for you, I expect them to come back. That means the current should be exactly the same in a CV circuit. Okay, so let's go back to Pizza Hut. So let's go back to our note today, so which is right here. So CV circuit, right? So in the CV circuit, the current, the I total, I1, I2, I3 should be exactly the same as I total. So let's put that down. So I total, which is the amount of current, the amount of electron leaving the battery every second, should be the amount of electron arriving at the location resistor 1 every second, should also be the same amount of electron arriving at location 2 every second, should also be the amount of electron arriving at location 3. I sounds like a broken record at this point. Okay, so in CV, we have these 2 equation sets. How about resistance? Voltage, current, resistance, right? Okay, resistance is like traffic, okay? It's like traffic. So I like to think of it this way. If I want to, okay, so imagine that each of these is a traffic jam, maybe a traffic light, so that it has like a wait time, right? So let's say the first traffic light has a wait time of 2 minutes. So this one has a wait time of 2 minutes. The second one has a wait time of 2 minutes, and the third one has a wait time of 2 minutes too. Well then, if I'm combining all 3 of them into a single one, so let's say I want to just combine every single one of those resistor into this one giant resistor, and I'm going to call it the R total. This is called the equivalent resistance. So it's one resistor to replace all 3. So let's say I don't want to have money to buy 3 resistor. Can I just buy one large one and replace it and do the same thing? Yeah, you can. Buy that one. Buy this one right here. You can replace those 3. So, but if I want to keep the amount of wait time exactly the same, then how big should that resistor be? Well, if the first resistor has a 2 minutes wait time, second one has a 2 minute wait time, third one has a 2 minute wait time, then if I want to buy a single resistor that replaces all 3, then I should have a 6 minutes wait time, right? So this resistor is just equal to the other 3, R1, R2, R3 combined. Okay, so think about it that way. All right. So for example, if this is, let's say, let's give you some real numbers. So let's say this one is 2 ohm. You know what? For current, let me use, for resistance, let me use a different color. So let's say this is a resistance of 2 ohm. R2 is a resistance of 3 ohms. And R3 has a resistance of, let's say, 6 ohms. Then in that case, if I want to replace all 3 with one single one, yes, I can do it. 2, 3, 6, 2, 3 is that. So I will replace this with a resistor that has resistance of 11 ohms exactly. Okay, just adding the 3. So it's like traffic jam. You going through lineups, right? It's like traffic jam or going through lineups. If the first one takes you 2 hours to wait, second one takes you 3 hours to wait, the third one takes you 6 hours to wait, then if you want to go through all 3 of these, let's say maybe you're going to Disneyland, so they have like insane wait time on some of the games. Not right now when it's like normal. So how much is the wait time in total? Well, 11 hours, right? So if you're combining all 3 wait time into one, then it's going to be 11 hours. Okay, so now there we go. Okay, now so for resistor, for resistance, what we do is add them up. So R1, R2, R3. Okay, now you can have more than 3. Of course, you can have more than 3. But, if you only have 3 and they're collected in series, this is what the diagram looks like. Okay, so next one, parallel. What if I can have more than one pathway for the electron to go through? Now this, we have to consider splitting electrons. Now, so we have a picture like this in here, but I'm going to start by explaining with our pizza diagram. So let's go back to our pizza picture from last day. Here we are, our pizza picture from day 1's note in the parallel collections format. Okay, So in here, we have more than one pathway now. So we can actually go here, go here, go here, go here, and then go here, go. Oh, actually, if you want to draw it exactly the same as the one that's in the book, then I should go like this and then split it off like that. Like exactly the same as the one that is on the other page, but it's exactly the same thing. Now this picture, don't get me wrong though, this picture is exactly the same. There is no difference between this one and this. Okay, there is no difference between these two. Now you might think, oh, okay, there is a difference because they're wired slightly differently, but they're actually the same. For example, electron. So for example, now let's look at the electrons. Okay, let's look at the electrons. So let's say this time I'm going to pick up, let's talk about voltage first, right? Voltage. So this is going to be V total. And then this first resistor or first house is going to have a V1. And this is going to have a V2. And this is going to have a V3, which is the amount of energy that you're depositing onto those houses. Okay, let's look at voltage. Now, think about what is voltage? The pizza, right? The energy. So we're going to do it for pizza. So let's make this 9 volts. So 9 pizza. 9 joules of energy per coulombs of electrons. Okay, so these all carries 9 volts. So imagine that you have an electron. Let's say 1 electron. So for now, so let's say you have 1 electron. Okay, so the electron is going to exit here. Okay, and it's going to pick up 9 joules of energy on his backpack. Okay, so it's going to have 9 volts on his backpack. Now, what would this electron do? So this electron is going to go like do 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 do. Oh, this electron has arrived at something we call junction point. At this junction point, the electron cannot multiply, right? The electron has to pick something. So the group of electrons, remember they go by coulomb, has to pick something. They have to pick to go either in this path like this, or some electron could go this way if they want, or some electron could go this way if they want. But they can't go through all 3 ways at once. So let's say you have an electron that decides to go into house number 1. Then that electron is going to go arrive at this junction point, decide to pick the left hand side, and then go through house number 1. Now, as it goes through house number 1, think about it. How many pieces is it carrying right now? 9. How many pieces will it have after it goes through the house? Now, you think about it this way. Does that electron have any other place to go other than that stop of the house? No, right? Think about it. The electron is going this route. I'm going to highlight it. The electron is going this route. Okay, the electron is going this route. So when you're going this way, you have to, now, so you pick up 9 volts. You start from here, you pick up 9 volts, and then you go this way. And then what happened? So before you go in, you have 9 volts. After you go in, you should have 0. Because the next stop that you're going to make is Pizza Hut. You will go back to Pizza Hut. So just before you enter, you'll have 0 volts. After you exit, you'll have 9 volts. You have 9 pizza. So then you do it again. You go through this, you drop your pizza so that you go, before you go in, it's 9 volts. After you go in, it's 0 volts. And then you go back to Pizza Hut and you pick up 9 more pizza and you do the whole job again. So this electron will actually drop 9 volts at the location of the first house. Okay. Well, then you will say, well, then does that mean there's no one going into the second house? No. Remember, we can send out more than one group of electrons at a time. Remember, those electrons are very tiny. We're counting by coulomb, but there are millions and billions and billions of them, right? So some electron, like you can think of it this way. So maybe I have like this electron in here, which is going that way. But then I can have this electron in here, right? and I can have this electron in here. So they're all different color. Okay, I can hire more than one person to deliver food for me, right? So then what happened is the three of them, okay, so the three of them arrive at some junction point. So they're going to go shuffle, and then they're going to arrive at a junction point, and that junction point is going to be here. Now, at this moment, the three of them is going to pick something. So they're going to say, okay, so where should we go? So maybe the green one with its 9 pizza goes this way. Well, then the red one with its 9 pizza goes this way. And the blue one with its 9 pizza, or the purple one, goes this way. So you're going to have 3 delivery guys or ladies with 9 pizza on their backpack each. Now, why would they all have 9 pizza? Shouldn't they have, like, for example, some people in here is going to say, hey, why aren't they... Okay, so I thought Pizza Hut gives you 9 pizza, so shouldn't they all have, if you send out 3 people, shouldn't they all have like 3 pizza each so that it makes... No, it doesn't work like that. So this battery, whenever it sends out electron, it's always 9 volts of energy per electron. So imagine that you're a Pizza Hut and you're only sending out 9 pizza at a time. You set it. So you're the owner, so you can set that number, right? So you hire 3 people to deliver pizza for you, and then you give the first one 9 pizza, you give the second one 9 pizza, you give the third one 9 pizza. Okay, so you're only giving them exactly 9 pizza each time. Now, then the electron have 3 different houses that they have to deliver to. So they're going to say, oh, at this junction point, why don't we just split up, and I will go to the first house, red, you go to the second house, and purple, you go to the third house, and then they all order 3 pizzas. So it will be 9 votes for all 3 of them. Okay? Because these 3 electrons, after going through that point, is going to have 0 votes on them. All 3 are going to have 0 votes on them because they have to be empty-handed before they can go home. So they're going to be going like this, and they're going to meet together, and they're all going to be empty-handed, and they're going to say hello, and they're going to go back to the Pizza Hut and pick up 9 pizza each and do this again. So the voltage drop across any parallel resistors has to be exactly the same. Okay, the voltage drop across any parallel resistor must be the same. Now, of course, it kind of doesn't have to be exactly the same as the one that's in the battery. That is not always the case. We will see some more complicated circuit later on that hopefully... So for example, like, you have to think about what happens if there's another house over here. What if there's another customer? Like over here. What if there's one over here? Think about it. So does house 1, 2, and 3 still eat 9 pizza? Think about it. They don't. They can't anymore, right? Because the electron with 9 pizza have to stop at that house number 4, the new house, first. And the electron must deliver something over there. And whatever that's left is going to be delivered to house 1. So maybe the first house eat 2 pizza, so house 1 will eat 7. Then the red one will do exactly the same thing. The red one will also deliver 2 pizza in the first house, and then house 2 eats 7. Same thing as the last one. So it doesn't matter how much you have to deliver at the beginning. Once you get to that parallel junction point, it's always the same for the 3 parallel path. Okay, let's go back to the note and fill in that voltage part. Okay, so for voltage, we have V1, V1, V2, V3, and they should be the same thing as V total. V1 is equal to V2 is equal to V3. If you look at that equation, it looks exactly the same as the current equation up there. Okay, but you can't just memorize these equations. It doesn't make any sense. You get very confused. You have to actually understand why, right? So you pick up something in here, you must drop it over there. You must drop everything over there. Why? Because this is your delivery route. You can't get to another customer. You might say, well, Mr. Chan, why can't I just do this? Then I will go to the another customer. No, you can't do that because there are people coming down this way, right? There are already people going down from here, like this way. So if you decide to go this way, then by the time you get to like this point, you can go up. If you go up, you're going to run into the people who are already coming down from upstairs, right? So you're going to meet there. For example, if you have a green path, then the green path is going to meet here too. So it goes like this. So you speed up over here at the junction point at the top, and then you meet back over here, and then you join force and you go back to the B side and you do it again. So you cannot backtrack, okay? Because there are other people already running down from there. So therefore, you can, in this situation, you can only have one delivery route. And so you can only pick one out of the three. So therefore, voltage 1, 2, 3 must be exactly the same. Now, how about the current? The current is actually very interesting. We already said that word a couple of times earlier, which is splitting up. I did mention splitting up, right? Remember, the current is the amount of electron actually doing this job for you. So for example, let's say this total current is 5. Let's make it a number that, okay, let's say this total current is 7 amp. Okay, so what does that mean? I have 7 groups of electron going through a point in the circuit every second. So so this is Pizza Hut, right? So when the electron leaves the Pizza Hut, there are 7 of them. Okay, so there are 7 of them. So it turns the corner. When it's on the top, it's still 7 of them, right? Okay, so then the 7 amp arrive at this junction point and do what? They have to split up. Remember, they have to split up. So the electron have to split up into these 3 paths. So maybe one electron would go this. So some electron would go this way. Some electron would go straight. So let me split up by using a different color. So some electron go this way. Some electron go down. Some electron go to the right hand side. Okay, so you have I total, okay, and it's going to split up into I1, I2, and I3. So I'm going to call them I1 going into resistor number 1, I2 going down to resistor number 2, and I3, the amount of electron going through resistor number 3. Okay, so I1 and I2, I3 must be equal to what? Together, they must equal to I total. Because remember, the currents are the number of people delivering pizza for you. I send out 7 people, 7 electrons, and they arrive at this junction point, 7 electrons. How many electrons leave that junction point? Think about it as a row, right? So like a row. And I have 7 people, 1, 2, 3, 4, 5, 6, 7. And they're all going down this row. And I have 3 pathways for them to actually exit that junction point. So how many people should exit that junction point? So you have 7 amp in. How many amp go out? I mean, it only makes sense if the amount of people going out is also 7, right? So let's say, for example, maybe like 4 go this way, 2 go this way, and 1 go that way. So you have like something like this. Okay, this picture makes sense. Any other number, now of course you can mix and match number. So this is going to be 4 amp out, and this is going to be, now remember, that is just the amount of electron, right? Groups of electron per coulomb. So 7 coulombs of electron goes in, 4 coulombs go to the left, 2 coulombs going to the right hand side, so 2 amp, and 1 coulomb goes to the bottom, so 1 amp. They must add up to the amount of electron, to the amount of current that enter the junction point originally. It must be, right? It's just conservation of things. I mean, electron, pizza delivery guy, doesn't matter. I send out 7 people, and they're splitting up. How many of them should come back when they rejoin each other? 7 people. Again, you don't eat the people who give you the pizza. You eat the pizza itself, right? So I1, I2, I3 must equal to I total when they add back together. Okay, so let's put it in here. I1, I2, I3. So I1 plus I2 plus I3. So in a parallel circuit, I1 plus I2 equal to I3. Okay, which is exactly the same as the voltage. So they're actually switched. So you can memorize this equation. It's confusing if you try to. Now, unfortunately, the resistor, the way you add resistors in parallel is actually a equation that hopefully you learned earlier in science class. But let me remind you, it's actually a really weird equation. It's 1 over R total. So it has a 1 over in it, a reciprocal. So it's 1 over R total equal to 1 over R1 plus 1 over R2. So they're all reciprocal, plus 1 over R3. Okay, now I won't go too deep into the math of why this is the case, but I want you to think about it this way. I have an analogy that I like to use sometimes. So you know there are 3 bridges that goes to Vancouver from Richmond, right? There is the Alpha Link Bridge, which is also called the Grenfell Street. It goes to Grenfell Street in Vancouver. There's Alpha Link, which is this path. Okay, so let's say you can go to from Vancouver to Richmond. You can take 3 bridges. So this one is Alpha Link, and this middle one is the Oak Street Bridge, and the last one is the Light Street Bridge, right? The Light Street Bridge, which is near our school. Now, if I tell you this, so let's say if you only use the Light Street Bridge, the traffic is going to be 10 minutes. So let's say 10 ohm. If you use the Oak Street Bridge only, so assuming that the other 2 bridges are closed, right? You only use assuming that the other 2 bridges are closed, only using the Alpha Link takes 10 minutes to go to Vancouver. Now I'm going to assume that Alpha Link is closed and Oak Street Bridge is closed. Then, and the Light Street Bridge is closed. So now we are going to have a wait time of, let's say, 20 minutes. Okay, because Oak is usually more busy. And again, same concept. If the other 2 bridges are closed and only one bridge is standing, which is the Light Street Bridge to Vancouver, and that will take us, that one has a lot of traffic. So let's say that would take 60 minutes, 60 ohms. So these are the resistance value, right? So in a series circuit, those will add up, right? 2 minutes, 3 minutes, 6 minutes become an 11 minutes wait time because you have to go through each bridge sequentially. So you have to go from one to another to the third one. But if you are trying to go from Vancouver to Richmond, you don't have to go through all 3 of those options, right? You just pick one. So adding more pathway doesn't increase your wait time. So let's say the government tomorrow allows that they want to build a 4th bridge, like from Richmond to Vancouver. That doesn't mean your wait time will increase, right? Because those bridges are not in series. They are in parallel. You don't go through all of them. You pick one and go through one of them. What will happen to the overall traffic when the government actually for example, put one more bridge over there? It should go down, right? See, that concept actually makes sense. The more the pathway, the less the wait time on average, right? So in series, because those are traffic jam, and you have to go through 3 bridges, one by one, because there's only one way to go through all of them, adding more resistor will add total resistance to the circuit. But in a parallel way, adding more resistor is adding more pathway. Adding more pathway actually lower the total resistance. So the more the merrier. This equation gives us exactly that. R1 plus 1 over R1 plus 1 over R2 plus 1 over R3 equal to 1 over R total give us exactly that. The more resistor you add, the lower the total value of the total resistance. You actually get a lower value the more you add. If you add like even more, like add another one, R4, R5, this R total will get smaller and smaller and smaller. That's what this equation can do for you. So that's not something you have to remember because the math to derive that is kind of beyond our scope, the scope of this course. So we are not going to do the deriving of this last equation. But trust me, and I think I have argued success. Well, I think I've make a pretty good argument about the fact that the more resistor you add in parallel, the more pathway you have, the lower the total resistance. Okay, so let's write that down. So adding more pathway always decrease the total resistance. So always decrease the total resistance. Now, if you decrease the total resistance, you'll be able to increase the current. Why? Remember, current are the electron that I'm sending out. If there are a lot of traffic, I can't send out too many people because they will be stuck in traffic. But if the traffic is really, really smooth, then I can send out more people without worrying about them getting all stuck in a row, right? So adding more pathway will always decrease the total resistance of the circuit. And because of that, I can send out more people. I can send out more current. So a battery can send out more current when the total resistance is lower. Okay? A Pizza Hut is willing to send out more delivery guys if the traffic jam, if there are more pathway that I have to deliver items to. More pathway also means that I have to, cater to more customers, right? So I will send out more resistor because of that. Okay? And because the traffic is good. Okay. So now that covers basic concept that, some of you might have learned pretty well in previous science class. Some of you might see this as a refresh, like a reminder. So that we can just continue with some basic solving basic circuit diagram tips. So first of all, if the question doesn't have a circuit diagram to begin with, you draw one. So draw a circuit diagram if not provided. Now, then you look at the resistor and the batteries. Links to each resistor indicate voltage, current, and resistance. Now, you might also want to label them with like a number. So for example, if you have one resistor, of course, you can do VIR. But if you have like many resistors, then you can do V1, I1, R1, V2, I2, R2. Next to the battery, write down I total, V total, R total. The battery is the Pizza Hut. It gives you the maximum amount of pizza when you go through it, right? So our V total, it also gives you the total number of people you send out at the beginning, right? So immediately next to the battery, you have I total, V total, R total. Now, R total is not something that you can, if it's a series circuit, you can see it immediately, but sometimes in a parallel circuit, you have to use that equation to calculate it, right? This equation. Okay, so now then you apply those series and parallel rules, which we wrote down, those 6 rules up there for each resistor and battery. If you know, okay, now basically like that. If you know 2 out of the 3 between V, I, and R, you can use Ohm's law to solve for the last one. Okay, then use Ohm's law to solve for the last one. V equal IR, or I equal V over R, or R equal V over I, etc., 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 right? If you know 2 out of the 3, solve the third one with the equation, with Ohm's law. Now, sometimes you might have a circuit that is slightly more complicated with resistor in parallel, but also something in series, right? Parallel and series combined together. In this situation, it's very likely that you will have to first combine all the resistors together and determine the equivalent resistance. That means if you're replacing all the resistor with one big one, what will that be? Okay, so you might need to find the equivalent resistance for the parallel branch. That usually will give you a good first starting step. So for example, for the 2 parallel branch, I'm going to combine it into one, and then now these 2 are in series, and it's much easier to look at. So how can I combine those 2 into one? That's using the same equation that we have for parallel part. So for example, for the resistance, I will just add the R1 with R2, 1 over R1 plus 1 over R2. Okay, and then 1 over the answer. So the way I do it in my calculator, for example, let's call up a calculator. There you go. Okay, now, so let's say I want to add something. right? So let me show you the kind of how I do the math. So let's say one resistor is, let's put it here. So let's say this is this resistor is 2 ohm. This resistor is 4 ohms. So 2 ohms and 4 ohms. And I want to add them together into this with equivalent resistance. So what would I do? So it's actually something like this. So you have to, so you can start by 1 over, so you have R equivalent 1 over 2 plus 1 over 4. So I want to combine the 2 and 4. So R1, 2, R2, 4. So what happened is, use a calculator, just go 1 over 2, okay, plus 1 over 4, okay, and then that's 0.75. So you add them. So now the next step, you have something like this. So you have 1 over this is equal to 0.75. And then what happened is you do a switch between these two terms. Okay, so your equivalent resistance is equal to 1 over 0.75. So you take the answer that you just got in your calculator, right? And you do 1 over. And you recall the answer in your calculator. Hopefully you know how to do that. Or just write down that number and then you do 1 over that number. That's another way. So that's 1.3 repeating. So the equivalent resistance is 1.3 repeating in this example, okay? So 1.3 repeating, which I would like to point out something funny though. Look at the 2 resistor to begin with. It's a 2 minutes wait time and a 4 minutes wait time. But when you combine them, what is the total wait time? It's less than 2 minutes. It's always less than the smallest one that you're adding. Okay, your final answer in this equation is always less than the smallest one that you're adding. Think about it. It makes sense because just having that path alone has a 2 minute wait time. If you open a new pathway next to it, why would the wait time be longer than 2 minutes on average? Right? I mean, you can close the other bridge and the wait time is still only 2 minutes. You're adding one more bridge to it. Why would the wait time be more than 2 minutes? It should be less than 2 minutes, right? So it's always less than. So that's one way you can check and see if you actually did it correctly. Is if you're adding like things in parallel, the answer should be less than the smallest one that you just add. Okay, so if the smallest branch is 2 minutes, as 2 ohm, then your equivalent resistance at the end should be less than 2 ohm, which is in this case 2. Okay, so, it's 1 over R1 and 1 over R2, of course, this is a 2. And now voltage drop, parallel branch, voltage drop is exactly the same, right? So the equivalent resistance voltage drop, V1 and V2 is exactly the same. Okay, so for example, that means, so let's say the voltage drop in here is 2 volt, the voltage drop in here is 2 volt, then the voltage drop for the equivalent resistance one is also 2 volts. Okay, voltage drop is the same, no matter if you combine it or not in parallel branch. Current is, well, because there's a split, right? So the current goes in here, split up into these two pathway. So that means the equivalent, now then what about the equivalent resist, the current? So this current, I total, this current, I total, will split up into I1 and I2. So I1 plus I2. So in parallel branch, you have this junction point. So I1 and I2 should be, if you add them together, should equal to I total. So for your equivalent one, that's just the I total going through this because they no longer have the split, right? Okay, now, okay, so I'm gonna pause the video here, and I'm gonna have, if you the next video is going to have those 3 examples that we that is coming up in the next few pages. So there are some examples that I would do, and it's going to be on the next video, right? I'm just going to separate the notes and the video. Goodbye, everyone.